Alright, in this video we're going to learn about how atoms come together to form compounds and molecules. That's what Chapter 3 is all about. So Chapter 3 we're going to learn about how to predict the type of bonds that are there. We need a very important concept called electronegativity. We're going to learn how ions are formed, how electrons are given off and taken, and from that we're able to build how molecular structures are put together. And that's going to end with a discussion of Lewis structures and then naming compounds. A lot of important things we're going to discuss in this chapter. So we're going to learn about chemical bonds and how atoms can exchange electrons or share them to make these compounds and molecules. And so there's going to be a systematic way to do this, and you're going to learn that. So it all starts at this concept of chemical bonding that's based on electron configuration. We've been learning about how electrons are configured, and that's going to be very important so we can learn how to put things together. First and foremost, though, can you figure out, by looking at the periodic table, what is a metal and what is a non-metal? Now, don't get too distracted by those metalloids sitting there in the green. So you can see all the blue things. Your alkali, your alkaline, transition metals, your actinide, lanthanide, all are metals. Being a metal gives those compounds certain properties. One of them is they like to give electrons. Nonmetals, on the other hand, as you can see there in those sort of the yellowish brown colors, they like to take electrons, and that's very important. And you see the green there, there's just, 6 that are considered metalloids. Oftentimes they're fall into the non-metal category for our discussions here. In the technological world, they're in between, depending on the products that are being made with them. You must know what is a metal. I should be able to show you any element, and you tell me if it's a metal, metalloid, or a non-metal. So you got to be able to memorize this. You got to be able to do this quick, fast, because we're going to come at it frequently. If you're still going, I don't know what a metal is, I don't know what a non-metal is, it's purely memorizing which parts of the periodic table that is. You're going to be tripped up. You cannot process what I'm saying if you can't figure out these designations for the grouping on the periodic table. So let's practice a little bit, okay? So I'm going to show you an element. You got to say metal, non-metal, or metalloid. Okay, it can be none of the above. Here's our periodic table to help. Okay, so I'm going to throw out some things there. Sodium, what do you think? Where is it at? Get used to finding it. It's over there, group 1A, and it is right around there. So there is sodium. It's blue. It's a metal. Okay, chlorine, where is it at? You got to go find it. Get used to knowing where it's at. It's over here, non-metal. Iron, there it is, Fe. That's a metal. Nitrogen, non-metal. Sulfur, non-metal. Strontium, we're over here, blue, metal. Magnesium, there we go, metal. And chromium, there you go, metal. Not too hard, that's how you figure it out. And if you can know that, we can make some good choices on how to predict how these elements are going to come together. There are the answers on the screen now. All right, 2 major types of bonding that take place between elements. One of them is ionic, where an electron is completely taken away from one element and given to another. Or there's covalent, where they share electrons between 2 atoms to form strong bonds. We're going to be able to recognize when elements do this. And there's some very good rules that we're going to be able to figure out. One of them is, of course, the metal, non-metal, and then we're going to learn another concept for that. Some other notes here about how we use the term compounds and molecules, and we'll get to that a little later. So we're often going to see these 2 extremes, but as with most things in life, something in between may be a better description, a little bit of both. As my kids like to say, I'd like a little bit of both. The concept we need to be able to distinguish between ionic and covalent bonding is this idea of electronegativity. So Linus Pauling proposed this idea of electronegativity, and it stuck because it works really well. And it's given the Greek letter chi, and it's a measurement and of an element, an atom, and its ability to attract an electron. So the higher this number, the more likely that element is to gain an electron and become a negative charge. The lower the number, the more likely it is to give an electron. And so, depending on how you do the measurement, you get slightly different numbers, but we're going to look at one set of numbers that really ranges from 0 to 4.0, and 4.0, just like our GPA, is a really high electronegativity, and there's pretty good trends that we see on the periodic table. And this is a measurement of the atoms based on how these elements are behaving in bonds rather than just on their own. So this is why it's better than the idea we didn't talk about before, electron affinity. Electronegativity, you can see in this periodic table chart that over on this part of the periodic table where we have all these metals, they have really low electronegativities, and as we start heading to the right and up, we find fluorine with the greatest electronegativity. And second is oxygen, 3.5, chlorine, 3.2. You need to memorize those numbers. We will refer to them frequently, and you need to know who the top three is: fluorine, oxygen, and chlorine. If we can know something about their ability to be very electronegative, then these molecules, as you can see, the nonmetals tend to have higher electronegativities, and as you get to the metals, they tend to have lower negativities. So in fact, some would say these are electropositive as we're going through there. So depending on the chart, the one that you look at, you're going to see some slight differences in the numbers, but the trends are always the same. So here's a figure that's probably in your book, and the height these columns are for the elements, you get an idea of how much electronegativity that's there. And so what we're going to do with these electronegativities is be able to take two different elements and compare their electronegativities and figure out the difference between them. And it's that difference that tells us something about the bonds that form between them. So fluorine has the maximum. It's the most electronegative. It's also one of the smallest elements, which means it wants to take on some electrons, has the highest ionization energy, doesn't want to get rid of them, it wants to take them. The other thing that's important about knowing electronegativity is we're going to use that to choose what element may be in the middle of a bunch of other atoms for molecules. So not only are we going to be able to tell something about the type of bonding as elements bond with each other, but we're going to be able to tell something about how to arrange them from this term electronegativity. And so when we put two elements together, they're going to form a bond, and depending on their differences in electronegativity, we can make a determination of what's called the bond polarity. Polar is one side positive, is one side negative. This is what we're going to be able to do with this. So polar, just like our planet has poles, bond's going to have poles. Maybe one side is more negative, one side is more positive. So if we go look at an electronegativity chart, we can figure out the electronegativity of each of these elements in these two examples. So oxygen's 3.5, and for electronegativity, the chi, and then hydrogen's 2.1. So we can take the difference here. Now the order doesn't matter. We just need to know the magnitude, the difference between them. It's 1.4 for those two. And we can see now fluorine being the most electronegative, it's 3.5 minus 4, and you say, oh, that's -5. Once again, we don't care about the sign. We want to know the difference between those two numbers. So think of it as an absolute value determination. Okay, the order doesn't make a difference because in space, I could have put the fluorine first and then the oxygen. So you got to think like a molecule. It doesn't really matter which way it's arranged. We just need to know the difference, and that's the important thing. So because there's a greater difference in electronegativity between oxygen and hydrogen, we'd say that bond is more polar. The oxygen atom wants to take more of the electrons. It's more electronegative. The hydrogen will want to give those electrons. The difference between oxygen and fluorine is not as great, so that does not have nearly the polar bond. Our notation for this then is to use this Greek letter delta. It's a lowercase d, and so that means a partial negative charge starts to form in this oxygen. We also could use the hydrogen, this delta plus here means a partial positive. It's not a full positive charge. This is not a full negative charge. And we can do that same thing, and that flips over here now because with oxygen and fluorine has the greater electronegativity than oxygen, and so it's going to pull the electrons to its side. We can also use what's called a dipole arrow, and you can see it's an arrow that points to the more electronegative atom. And then we put a cross on this side so it looks like a plus sign. And so depending on how the atoms are arranged, the polarity of that bond can change. So you can't make determinations and go, oh, oxygen is always the most electronegative. It may be in most cases, but when it's partnered with fluorine, then it changes and becomes a more positive side of the bond. So you need to be able to look at a table and get a general trend on what the numbers are. Once again, I encourage you to just memorize the electronegativity numbers that you've seen here for oxygen, fluorine, and chlorine. You're going to see hydrogen and carbon a lot, so we need to do that. Now, books and drawings and scientists, everybody, we kind of do things just a little bit differently, how we draw them, how we show them, this polarity. One way could be these partial charges with the delta. We talked about the dipole arrow, but you may also see some what's called charge distribution plots, where it's more red, that's more electronegative, and where you see blue, that's more of the positive area. And those are from computer models, and those are nice ways to visualize the electron density relative to the molecule that we're looking at. Now, in order to distinguish what type of bond is being created, we can use the electronegativity difference, and it falls into three categories. First is if the difference is about 0.4 or less between those two atoms, they fall under what's called the covalent or nonpolar category. This is where the electrons want to share, the atoms want to share electrons with each other. If the difference is greater, such as 0.4 to 1.7, then this falls under what's called a polar covalent. The atoms are pretty much sharing the electrons, but one is taking more than its fair share. And so that becomes a negative side, and the other side's positive. If the differences around that are greater, then this forms an ionic bond. Now, I wish chemistry was just this straightforward. You can just look at these numbers and that is it, and go home, school's over, session's done. But there's one other concept that we have to bring into there to figure out exactly if something's ionic or covalent. And this is where we need to know if something's a metal or a nonmetal. In this chart here, this gives you an idea of deciding whether something is ionic or covalent. And you can see on the x-axis, this is that difference, the delta chi is here. And then percent ionic character tells how much something really is ionic or not. So that number we were talking about before is about 1.7, so that'd be right around here. Now, what we see here in this chart, that everything that's kind of got that blue color, HCl, HBr, HF, all these things, these are considered covalent compounds. While these that are sort of in that reddish color, this maroon color, those are considered ionic compounds. And it would be nice if there was a line somewhere right around here, that 1.7 line, that if we crossed over, it'd always be ionic. And if over on the left side here with low electronegativity differences, that it would be covalent, polar covalent in that case, or down in the covalent area, nonpolar covalent. But it's kind of blurry on this line right here, and it's blurry. The blurriness can go away when we think about if something's ionic or not, if we understand if it has a metal and a nonmetal. Now, hydrogen's one of those tricky things, but for the most part, it's considered a non-metal. And so all these that are blue are nonmetals with nonmetals. So even though they have a larger electronegativity difference, it is still considered a a polar covalent arrangement between hydrogen and fluorine. It's mainly sharing. Now you move up here to lithium iodide, lithium bromide, and all of these up here, even though they have electronegativity difference that's less than 1.7, it's probably 1.5 and 1.7 and 1.8, these differences right around here, these are still considered ionic. You'd say, well, those numbers are less or right at 1.7, so it has to be polar covalent. Well, we have to use another concept, and this is the metal-nonmetal. These are all metals with nonmetals. And so if they have that characteristic, we're going to first label them as ionic. So we've got to bring a couple concepts together, especially right around this blurry middle line. So if they're metal-nonmetals, that's going to be ionic, even if their electronegativity is slightly less than 1.7. If they're two nonmetals together, covalent. Polar covalent if they're near that dividing line. So that is a good starter to start thinking about chemical bonds using electronegativity. In our next little series here, we will talk about the types of covalent chemical bonding and ionic, and go over some examples here with metals and nonmetals. So that's electronegativity in our introduction to bonding.